Hello everyone. In my last two videos, I tried to show two different coil gun circuits, one with an SCR switch and another one with a MOSFET switch. In both of these circuits, one thing is common, that is charging a 4000 microfarad capacitor with a 160 volt power supply. So to get the 160 volt supply, I used in my previous circuits a transformer, a rectifier and a capacitor. So the overall supply becomes bulky. But there is another way of getting high voltage, that is using a boost converter. Here I have one. It converts 12 volt to 150 volt easily, and you see the few components are needed and it is very light. I'll try to explain in this video how you can make your own boost converter. This slide shows the basic coil gun schematic with the high voltage source. And I am going to use a boost converter to convert 12 volt to 150 volt to replace this supply. The heart of a boost converter is an inductor. When an inductor is powered, current starts to increase from 0 to higher and higher current. And if suddenly the switch is opened, the sudden change in current, or we can say del I by del T, becomes very high. As a result, we can get higher voltage across this inductor. This is the basic principle of generating high voltage. So in a boost converter, energy will be stored in an inductor. From the source, the charging current is shown with red line. After some time, the current is allowed to go down much faster than the rate of rise. During the first decay of the inductor current, the energy is released to the load. I would like to tell you an old story of mine. Decades back, I was telling a person that with only a large inductor, even with a small 1.5 volt battery, I can generate enough high voltage to give you an electrical shock. He didn't believe me. Then I used this circuit and told him to touch the two terminals of the inductor with his two hands. When I made and break the contact of the circuit with a 1.5 volt battery, the electrical shock he got will never forget. This is the basic circuit of a boost converter. When the switch S is closed, current starts flowing through the inductor. The rate of charging is shown by the red line, V in by L, where L is the inductance of the inductor. When the switch is released, the stored energy in the inductor is going to the load and the capacitor through this diode. The discharge rate is shown here, V out minus V in divided by L. As the switching on and off process is repeated again and again, slowly the output voltage go higher and higher. In practical boost converter circuits, the mechanical switch is replaced with a MOSFET or other electronic switches. Pulses applied to the MOSFET gate switches it on and off. The switching frequency and the duty cycle, these two terms we'll be using from now on. During the MOSFET on time, the inductor is being charged. The peak current at the end of the on time is expressed by equation IP equals V in by L, D by Fs. During the MOSFET on time, the current falls from the peak to the bottom, and peak current can also be expressed by this equation. Equating these two equations, we can find a very important relationship, that is output voltage equals input voltage divided by 1 minus duty cycle. This means that changing the duty cycle, we can increase the output voltage, which is much higher than the input voltage. This slide shows the plot of output voltage against the duty cycle D. The equation tells us that if D approaches 1, we can get thousands of volts at the output. But in fact, there is a maximum limit due to various practical effects. The inductor resistance, MOSFET drain to source resistance, diode voltage drop play important roles as limiting factors. In practice, close to 100% duty cycle, the output voltage first levels off and then starts to decrease. In my case, I found a maximum limit was 190 for my circuit. So for our coil gun, we need a 4000 microfarad capacitor to be charged up to 150 volt. We do not need a fast charging. Let us consider time to charge is 1 second. So the energy to be stored within 1 second at the capacitor is half CV square. In our case, the VC is 150 volt, so energy becomes 4.5 joules. So the power requirement, energy by time, becomes 4.5 watt. Usual efficiency of a boost converter ranges from 85% to 95%, depending on how well we choose the components. Considering 90% efficiency, so this is our output power, and input power should be around 5 watt. This is the schematic diagram of the practical circuit that I tried. A 555 timer IC is used as a PWM pulse generator. Its frequency is set at 20 kHz with the capacitor C3 and the potentiometer RV1, whose value is 10 kilo ohm. As the potentiometer is varied, the duty cycle changes from minimum to the maximum. The two small transistors serve as a MOSFET gate driver. Very important selection should be done with these two components, the MOSFET Q3 and the diode D3. Both should be rated for higher than 200 volt, as our output voltage is around 150 volt. This is the practical circuit on a PCB, and this is the 555 timer IC, and this is the potentiometer. By varying the potentiometer, we can change the duty cycle. And this is the inductor, 220 microhenry, and this is the PN-PN-PN pair to drive the MOSFET, and this is the MOSFET, and this is the high speed diode. Previously I tried this 110 volt and 160 volt power supplies with my coil gun. So these are replaced by this small boost converter. So this is our original coil gun circuit, and this is the capacitor that should be charged with higher voltage, like more than 100 volt, to be an effective coil gun. And this is the boost converter, and at the input we are using only 12 volt, which can be converted to 50 volt, 150 volt, and that can be used to drive the coil gun. This is the whole coil gun system shown with the boost converter replacing the old power supply. The boost converter circuit is connected with a 12 volt supply, and you can see the output voltage and the voltmeter, and also the output of the 555 timer is connected with the oscilloscope, and you can see the PWM signal. And by changing the potentiometer, the duty cycle can be changed. You can see on the screen, and the output voltage is also going up fast. So this is the 12 volt power supply which is connected to the now the boost converter, and the output is connected to now the 4000 microfarad capacitor combination, and it is connected. Now you can see the output voltage rising a little slower than before. So as the output is kind of charging the 4000 microfarad capacitor, so I did not choose the components to optimize for fast charging, so the charging is a little slow now. But you can see that less than a minute already the voltage is reached 120 volt and it is going up. Once it reaches 150 volt, I can use it with my previous coil gun. So we are almost there, 140 volt now. $145 so the charging is little slower as it reaches higher and higher. So now we are about to reach the 150 volt, and once it is charged to 150, I'll be connecting it with the coil gun. You can see now the coil gun is charged with the projectile and it is fired.